Hello and welcome everyone to video lecture number 18. In this lecture we will be continuing our discussion on MOSFET scaling. We will be talking about the barrier model. So one of the models the barrier model we introduced in one of the previous video lectures when we first introduced the concept of transistors, and we will look into off-state current. Specifically, we will try to get to this idea that as we scale down our transistors, the off-state current of a transistor increases. In a smaller transistor, we have a larger amount of off-state current, and in a smaller transistor, we have a larger sub-threshold current, the current that flows below the threshold voltage. Alright, so some of the discussions that we will have today are covered in section 7.2 of the textbook by Chen-Ming Hu, which is available here in this website. Alright, so just to get started, let's review what we derived for the current voltage relationship in lecture 17. So here what we essentially did was we derived the value, the relationship, we derived this equation for subthreshold current, the current that flows when the gate voltage is smaller than the threshold voltage. And important feature is that this current is exponentially proportional to the gate voltage Vg, and also the way it's related to the drain voltage is through this factor 1 minus e power qvd over kt. So if we plot the current voltage characteristics where current is in linear scale, then below the threshold voltage we will not be able to see any current. This will look like it's zero below threshold voltage because the subthreshold current is so much smaller than the current that you will get above threshold voltage. But if you plot the IDVG curve where ID is in log scale, then we will actually be able to see the subthreshold current. So basically this is a plot of log ID. So the y-axis is actually log ID here. And an important feature that we said was that this subthreshold current is independent, almost independent of drain voltage, meaning that if we increase the drain voltage, this subthreshold current does not increase. The current above threshold voltage will increase, for example here, and here also there is a small difference. There is a difference in the drain current. We cannot see it because it's plotted in logarithmic scale, but the subthreshold current, there is a much smaller difference of the subthreshold currents in the subthreshold region, and so the difference between the subthreshold currents for different values of drain voltage is much smaller than the difference for currents above threshold voltage for different drain voltages. And the reason is that because of this factor 1 minus e power minus q Vd over q, this factor goes very quickly to 0 when Vd is of the order of Kt by Q. So if Vd is larger than 3 Kt by Q, there is absolutely no dependence of the subthreshold current on drain voltage, and as a result the subthreshold current does not depend on the drain voltage. So then we define two important MOSFET specs, the on current and the off state leakage. And on current means the current that you will get when the gate voltage is equal to the power supply voltage VDD, and also the drain voltage is equal to VDD. So basically this current is called the on current. Note that this IDVG curve is for VD equals VDD equals to 1 volts. So this value is the on current, and off current is the value of current for Vg equals to 0 and Vd equals to 1 volt. So this is the off current. Alright, so we'll see how this curve change as we go to small scaled transistors in this lecture and also the later lecture. Let's look at how the energy band diagram for a MOSFET looks like. Now we have seen the energy band diagram for a PN junction. Now a MOSFET is essentially two PN junctions. The channel you can consider going from source to drain. You can consider that as two PN junctions connected back to back, because you have the P-type source here, then you have the N-type source here, then you have the P-type channel here, and then you have again the N-type drain here. So you have one PN junction here and another PN junction here. All right, so first the energies for the source. So you have the conduction band, valence band, and it's N-type, so the Fermi level is closer to the conduction band. The same is true for the drain end. The Fermi level is closer to the conduction band, and on the other hand, for the the channel, it's p-type, so the Fermi level is closer to the Fermi level. All right, so in equilibrium, meaning that when you have both the drain voltage and gate voltage to 0, then the Fermi levels for the source, the drain, and the semiconductor channel will line up. So this is how it will look like. So if you fix the source and drain energies, then you shift the semiconductor energies upwards, so that the Fermi levels for all the three sections line up. And if you do that, this is how the energy band diagram will look like for a MOSFET. And what you can clearly see is that between the source and the drain there is a barrier, and what we do with the gate voltage is that we modulate the height of the barrier. All right, so before we see the effect of the gate voltage, let's see how the energy band diagram changes when you have a drain voltage. So say you have applied a drain voltage, and what will happen is that now the energy bands on the drain side will decrease, and the amount by which it goes down will be equal to QVD. So it will go down by QVD amount. And just for comparison, the red dotted curves are the energies before applying drain voltage, meaning that in these three red curves, the Vd equals to 0, and the solid black curves, you have a certain Vd, and the gap between this is QVD. So all the three gaps will be QVD. All right, so now let's see how the energy bands now change when you have a gate voltage. All right, so here you have, so this is the case when you have Vg equals to 0 and Vd larger than 0. All right, so now let's see you have applied a Vg. So now let's look at what happens when you apply a gate voltage when you have a certain drain voltage already applied at the drain. So again, for comparison, this is the case when you have gate voltage equals to 0 and drain voltage to some certain positive value. All right, so what you'll see is that now the barrier height has decreased, and the amount by which the barrier has decreased is equal to Q psi s. Okay, so we'll look into that in the next slide. But the important thing to note is that because this gate voltage is applied through the gate, what it does is that it changes the conduction band and the valence band positions, but it reduces, it keeps the Fermi level in the semiconductor at the same level. And this is how the carrier densities in the channel changes, because now the Fermi level, difference between the Fermi level and the conduction band has decreased when you applied a gate voltage. Alright, so for comparison, the red dotted curve is the value, is the EC when gate voltage is 0, and the black solid curve is the case when you have a certain gate voltage, and the amount by which the conduction band has gone down is equal to Q psi s, and similarly the amount by which the valence band has gone down is equals to Q psi s. Alright, so now the important thing to note here is that from the perspective of a barrier model is that now the electrons flowing from the source to drain sees a smaller amount of barrier when you apply a gate voltage. So for gate voltage of 0 volts, 0 gate voltage, you had a larger barrier. By applying a gate voltage, you have reduced the barrier height by Q psi s amount. So now a larger number of current can flow from source to drain. So this is the essence of the barrier model. Okay. What we are plotting here is essentially same as what we have plotted before. So, but we are just plotting the conduction band energy as a function of the position along the channel. On the left we have the source, on the right we have the drain, for just like previous case. Our purpose is to show in the later, by comparing this image, this figure with the figures that we'll show in the next slides for short channel transistors. Our purpose will be to see the difference of how the energy band diagram changes as we decrease the channel length. Alright, so here what we have shown is that for Vd equals to 0, the conduction band and the drain and the source are lining up, and there is a barrier in the channel. And as we increase the drain voltage, the conduction band edge in the drain goes down. But the important point to note here is that although we are increasing the drain voltage, the barrier from the source to the channel on this side does not change. In other words, the barrier height is independent of the drain voltage. Okay, so now if we apply a gate voltage, the barrier height changes for the electrons to flow from the source to the drain, and that is the essence of the model. The barrier height is modulated only by the gate voltage and not by the drain voltage in a long channel transistor. Alright, so now let's see what happens in a short channel transistor, or as we decrease the channel length. So here what we are showing here is that, say you have a transistor which has a channel length of 20 nanometers, and in that case the barrier height is this much, around 1 units. Now if we reduce the channel length to 15 nanometers, what you can see is that still the barrier region is almost the same as that for 20 nanometers. Now what is interesting is that as you go to smaller channel length, for example 7 nanometers, you see that the barrier starts decreasing, and as you go to 5 nanometer you can see that the barrier has decreased. And this effect essentially means that as you decrease the channel length, the barrier height becomes a function of the drain voltage. Remember, for a long channel transistor, the barrier height does not depend on the drain voltage, but if you have a short channel transistor, then you will have the barrier dependent on the drain voltage. In other words, as you scale down the channel length, the barrier height gets more and more modulated by the drain voltage. So to make that point, let's look at a very short channel transistor, 5 nanometer, and this is the barrier that we have, and this is for drain voltage of 0 volts. And now if we apply 3 volts, you see that the barrier has now decreased. Compared with what we have seen earlier for long channel transistors, the barrier was not decreasing as you were increasing the drain voltage, but for a short channel transistor, the barrier actually decreases. And this effect is called drain induced barrier lowering. Alright. In other words, in a short channel transistor, the barrier height is strongly coupled with the drain voltage. And what it essentially means is that as you increase the drain voltage, your current, the subthreshold current, actually increases. Now, although you are at the same gate voltage. So previously for long channel transistors, what we have seen is that the subthreshold current or the off-state current is independent of drain voltage, and based on the energy barrier picture, this happens because the barrier for the electrons or the minority carriers to flow from the flow between source and drain, that barrier height is independent of drain voltage for a long channel transistor. But for a short channel transistor, this barrier height becomes dependent on the drain voltage, and as a result our subthreshold current increases in a short channel transistor as you increase the drain voltage. So to make that point, let's compare the IDVG plots for a long channel transistor and a short channel transistor. So on the left we have a long channel transistor, and on the right we have a short channel transistor. Alright, so here what we see is that for two different values of the drain voltage, our subthreshold current is the same, because based on the equation that we derived, the subthreshold current is a very weak function of drain voltage when the drain voltage is of the order of kT by 2. So this black curve and the red curve actually falls on top of each other when the gate voltage is smaller than the threshold voltage. On the other hand, for a short channel transistor, what you will get is that as you increase the drain voltage, your subthreshold current also increases. For example, if you are at say 0.45 volts at drain voltage of 50 millivolts, you have this much of current, but as you go to drain voltage of 1 volts, your off-state current has increased by this amount, and because this is a logarithmic scale, you will see that this change is large. So you can also quantify this effect called the drain induced barrier lowering by the shift of the threshold voltage. So in this case, say the threshold voltage is the gate voltage at which you get a certain amount of subthreshold current or the off-state current. So at 50 millivolts, the subthreshold current, the threshold voltage is here, but when you have a drain voltage of 1 volts, the threshold voltage has decreased, and the amount by which the threshold voltage has decreased is a quantitative measure of this short channel effect called the drain induced barrier lowering. So to summarize, in a short channel transistor, the off-state current increases as you increase the drain voltage, and this essentially shifts the threshold voltage to lower values for a higher value of drain voltage. In the other hand, for a long channel transistor, the offstate current is independent of drain voltage, and so increasing the drain voltage in a long channel transistor does not increase subthreshold current by any significant amount, and the threshold voltage is independent of the drain voltage.